Mark is the head of, he's in Intel Manufacturing Technology, or Technology Manufacturing Group. He's a senior fellow, and he's in charge of CMOS process development, continuing to push process technology. He's always quoted whenever we have new process introductions. So please, all process questions that you have, Mark would be happy to answer. Rick Colson. I don't call him Richard Lee. He doesn't like it. That's when his mom is mad at him. And I know that. Rick is also in the Technology and Manufacturing Group, and he's the Director of Storage Technology. He's been doing a significant amount of storage work for a number of years. Ian Young, also in TMG, but he's in components research. And Ian's job is to look at how he can continue to extend Moore's Law for the next 10 to 15 years. And so probably one of the more fun jobs that we could all have. Rick and Ian, senior fellows. Intel fellow Ajay Bhatt. Ajay is the chief client platform architect in the client platform division. Pradeep Dubey. You don't care?
You go.
Michael. Pradeep is in the Intel labs, and he's Intel fellow in charge of the parallel computing labs. So he's the one who's been focusing on a lot of the parallelization for the Xeon 5 product line. Hong Jang, he doesn't look like Tom Piazza. He doesn't sound like Tom Piazza, but he is also an Intel fellow and a member of the in the graphics group in our product in the DPG video products group. Dr. Genevieve Bell, she will gladly point out that she's, quote, the non-technologist up here. She runs the user experience group in Intel Labs. She's an ethnographer and has a degree in anthropology. And her job is also to point out my character flaws at any time that she sees fit, which usually is just about every time we see each other. Fai Briggs. Fai is Intel fellow. He works in the server group, focusing on next generation server architectures and extending the server capability. And then Dr. Per Hammerland is also an Intel fellow. He's in charge of SoC architectures and our next generation CPU architectures, and contrary to what it says on the board, he works in the Intel architecture group. So anyway, so let's go ahead and get started because we have a few minutes. How this works is you ask a question. If we deem that it's worthy, we actually have a gift for you, and we're pretty lenient on that. Raise your hand. I'll call on.
So specifically the process for Ivy Bridge and Haswell, how do you handle soft errors? What's the strategy with that for caches, L1, L2, L3, the buses, the TOB caches, and as we start to use the GPU for more security type instructions, do those also need to have error correction and detection?
So there are several things we're doing. We're spending a fair amount of time, first of all, characterizing our silicon to know how it will behave. And then we work with Mark and his friends to make sure that we have the best process for any given year to handle soft error rates. After that, we do a fair amount of modeling to establish what kind of microarchitecture changes. Like you said, do we need, what kind of ECC, parity, and so on do we need to add on each of the structures? So for example, we do have parity for ECC on all of the data carrying register files and caches and storage in the processor. So it's a fair amount of characterization, process work, and microarchitecture that we do to make sure we have a good SCR solution.
So as we move to 450 millimeter wafers, that decreases the amount of cost that's from non-lithography steps, relatively speaking, whereas the relative cost of lithography goes up correspondingly. So does this mean that you will have to invest more heavily in driving down the cost of lithography, or is that just something you're willing to accept going forward?
Well, I think it's true in your statement that the cost of lithography as a percentage of the total wafer processing cost goes up in each generation, yes. And that the conversion from 300 to 400 millimeter wafers certainly address the cost of, reduce the cost of the non-litho steps, but litho may go up, may not realize as much of the benefit. But there's still some patterning steps that do benefit from conversion to larger wafer size. Yes, the stepper costs, you have to step more times across a big wafer, but resist coats, resist clean, the etch steps, all benefits in going from 300 to 450 millimeters.
So you don't see a corresponding necessity to increase wafer throughput, although it might be nice.
Well, that goes without saying. We want all process steps to increase the throughput.
Every tick-tock cycle takes about 3 years roughly, right? And you continue 2 years, okay? So you continually get better. When do you guys hit the wall where that 2-year cycle can no longer be met and you have to, for lack of better terms, reinvent the laws of physics to work around the physical limitations that you hit? Is that 3 generations of tick-tocks away? Is it 5? Is it 6? When do you think that happens? Because it has to happen, right? It's just a question of when.
I don't accept that it has to happen, but it probably will. But I think now we can see about 10 years out. I don't see the end of Moore's Law for more than 10 years. And I think we'll continue on the 2-year cycle for the foreseeable future.
If I may add, we have to have a pipeline of future options being worked on in our research, and we try to keep visible out, like as Mark said, as far as we can, multiple options of technology, generations of technology. But for the part that we can't see into, and you're predicting, maybe trying to predict that it will come to an end, we are trying to invest some longer range research in my group to look at what would replace, be another option for the transistor when we see MOS transistors falling short in energy efficiency and power performance. So we're putting resources into really taking care of what you're predicting may happen. We're not saying it's imminent, but we are actually hedging our bets to look even further out, and we're looking at devices that have faster turn on, steeper turn on, and more energy efficiency than the MOSFET will have in that future time, 10 years plus.
Barry, did you want to add something?
Yeah, just a quick, our tick-tock cycle is 2 years, every 2 years. And I think for me, one of the rewarding things about working at Intel is that we get to work through and solve some of these near impossible challenges to keep that cycle going, right? It's collaboration between architecture, microarchitecture, design, and manufacturing, right? Making sure we get the ideas from the labs and so on through into our products. So it's a lot of work. It doesn't happen for free, but that's the fun part.
Okay, next question. Could you stand up so we can see you?
Sure. All right, so my name is Murthy. I work for Emulex. So my question is on this Xeon Phi and Xeon processors. It seems, some of the speakers were talking about Xeon Phi both as a general purpose processor as well as a co-processor. So could you clarify, what's the main use model? And in the case where it's connected to Xeon, what's the connectivity? How do they link to each other?
Pradeep?
So it's a co-processor. It's attached to Xeon as a PCIe, and it's a general-purpose processor in the sense it's a capable processor, general-purpose processor, general-purpose core, so it can run pretty much any workload, which is highly parallel. All it requires is you to have enough parallelism in your application, in your code, so that you can actually trade off single-thread performance. That's the only difference. That trades off single-thread performance, you have simpler cores and more cores. But they're the same cores, same equally capable cores otherwise. So if you have more parallelism, enough parallelism, then you're willing to make that trade-off, then you would run your code on Xeon Phi.
But for the point in time when you hit the end-all component, you do want to use Xeon and the higher performance.
Absolutely. So anytime either you don't have enough parallelism, or the cost of going anywhere, right, over PCIe is the bottleneck, then AMDAL probably then you've never seen the benefit. And then it's not the solution for your application.
Hi, you wanted to add something?
Yeah, I also wanted to add that the major difference, the complementary products, you find Xeon Phi used today as a co-processor, especially for not only highly parallel but more bandwidth demanding, applications, and especially things that are vectorizable. That's really where we put a lot of the effort, both the parallelism, vectorization, and the bandwidth, to make sure that for those applications that don't fit in well with Xeon, traditional Xeon, Xeon Phi would be a coprocessor to accelerate those type of applications.
Okay, next question.
Dilip Bhandekar, Microsoft. It's great to see scalable server architecture and SoC architecture as the job description for Phi and Pair. So I wanted to know how you see server architectures evolving over the next, say, 5 years, and what role SoCs might play in that time frame, and how Atom versus Xeon plays in SoCs. Lots of questions.
Why don't you, hey, Friday, why don't you jump in?
Yes, we continue to look at Xeon, with the core architecture really targeted for things that really provide a lot of that single thread performance that is much higher. But especially when you start looking at, today the Xeon product we have deliver the performance with the number of cores that we have, and also the performance per watt. That will continue to be the case. We will see more of the SoCs, and Pearl can certainly add to it in segments where you need that density, that you don't currently have, for new form factors that are much smaller than what we have in our current Xeon.
So I think you were asking about how we can use SoC on the server line. For us, there are two sides to SoC. One that I think is good is that it's an opportunity for us to make sure that the developer interface to our processors is the same between even client and server, or different kinds of servers. The best way to be the same is actually to try to use the same components even. So some of the things that we're working on going forward is to make sure that we get reuse between the different product lines. So that's moving more of the development over to these SoC-like processes. But I think you'll see a convergence where it makes sense, and we'll stay diverged where the performance requirements calls for keeping it separate to reach the requirements.
The other part of my question, we didn't get to, the server platform architecture evolving over the next few years. Can you see disaggregation of pieces of the server?
Yes. So the question was, server architecture is evolving. Are you going to see disaggregation right now, where mainly server platforms consist of processor, memory, I/O, and storage, and they're on a common platform, and you do it through, say, levels of rack scale architectures? Yes, I do see disaggregation occurring, where storage, potentially even memory, and certainly I/O are disaggregated into different boxes, and you have a common interconnect that can go through those boxes, either through standard Ethernet or through a fabric that's optimized to be able to handle what we believe are going to be smaller message types than what you've seen before, because big data and a lot of the search algorithms don't need the large packet sizes, and we're seeing a lot of jitter in terms of the smaller messages getting behind larger messages as they get intermixed within an array. And so I think that we're going to start seeing an evolution of better fabrics that can actually handle and minimize that jitter as much as possible. Yes. They've been identifying the next question, so you're in the queue.
Richard Probst from SAP. Very happy to see Intel move into the fabric business with the TrueScale products and the teams that you've acquired to enter that business. And of course, a major source of latency is moving from the processor to the NIC. So I guess this is an SoC-related question to understand your thinking about moving the NIC on die, how you would do that, how that would relate to different protocol choices that people may be making, how that relates to open ecosystems and other fabric providers, and just other things you can say about that piece of evolution.
Well, there's not a lot I can say, actually. And, I will correct you on one thing. We've been in the fabric business for years because we have a very healthy Ethernet business, both with LAN on board as well as the issue. So, we're spending a lot of time working with governments and academic research on next generation of high performance computing. And the realization there is the targets that the industry's been giving is an exaflop of performance at a 20 megawatt power load, which means you only get 20 picojoules per operation to do work. And if you divide it out between CPU, memory, storage, and network and everything else, you get very little energy that you can dedicate to any one of those at any particular time. So the natural element is to understand what in terms of the fabric, not only the latency, but the energy, and the energy of being able to move that data from point A to point B. And the fabric is yet a key component of that. So a lot of the effort we're looking at is how can we bring that fabric into the management complex that we have CPU and memory in today, and be able to manage that so that we can meet these aggressive power targets that we've been given to deliver these systems by the end of the decade.
But I think the question is about 3D package technology or 3D chip stacking, which is a technology Intel is exploring and developing. But having the technology and having a cost-effective solution are two different things. So we can do 3D chip stacking, but I think the added cost is still a bottleneck in terms of saying, yeah, it's a compelling product. And you have to recognize that there are multiple ways of doing multi-chip packages. There is the 3D stacking using through silicon vias, where one chip is on top of the other. You can mix up a memory chip with a logic chip. But that's the most expensive solution. The older technology is package on package, where you've got two packages stacked on top of each other. That's already very commonly used in the industry. So it's competing against that lower cost solution. And there's also a multi-chip package where you can put two chips side by side in the same package, which is also a cheaper solution than the 3D stacking. So we have all three options, but which ones are more economical, more cost-effective for a given product is still to be decided in some cases.
But if somebody wants to consume this various level of packaging, would you see somebody getting a single package, so cheap, and including a very large bus level cache?
Were you asking if you want to have a very large cache in the same package?
Yes.
Well, you can do that again either by
side by side,
between 3D stacking or side by side, and there are pros and cons of each. I'm not going to say exactly which ones we're choosing, but you have to consider cost in that equation
And power.
and power. The problem with 3D stacking is that it may be an acceptable power solution for a 1 watt product, but it's not viable for a 30 or 40 watt product because you have no way to heat sink the heat out of that package.
Thank you.
All right, it's your chance. Stand up and be known by all.
Jack Clark from ZDNet. In a few years, it's likely that some form of non-volatile memory, like spin torque or memory store phase change, will have superseded flash. Will this have a knock-on effect on how you design chip architectures? And if so, what will that be?
Richard Lee.
Absolutely. All those technologies, as far as them being cost effective, or actually even working, many of them are still, it's not in the bag, it's a race. We don't know which one of those or others will be ultimately cost effective. There's some like phase change now you can get, but it's more expensive. So yeah, there are all sorts of things once you have that kind of latency. When we're talking about things that can do 1 microsecond of latency, it kind of changes the whole memory storage hierarchy. And you have an SSD that's like that, well, do you really want to use it as a block SSD, or you want to use it more like memory? And so there's a lot of efforts in SNIA, the Storage Networking Industry Alliance, for instance, about what API should be developed to take advantage of that kind of thing. So there's a lot of system work going on, and what ifs, and how would we do things if certain things come true. But the base memory technology itself is the biggest wild card at the moment.
Thank you.
Actually, to follow up, I'm Margaret Kiyosi from AT&T. So my question is about virtualization. So what does Intel see as the top 3 to 5 challenges that must be solved so that we can realize data plane virtualization?
Fine.
We're looking at a number of evolution from where we are today. There's no commitment directly to which direction we're going to be taking. But if you look at current virtualization, there are still some overheads that we would like to really reduce significantly. So we're going to see those evolutionary products that will try to continue to reduce exits, entry, into the virtual space, and that will continue. But right now, we haven't had any plans set out for 3 to 5 years.
So, and I'll answer your question, the top 3, VM migration, VM migration, VM migration. I think there's still significant challenges in terms of the I/O architecture and how you're going to migrate that, not only from machine to machine with inside the rack, but inside the data center and data centers abroad. I think there are a lot of solutions, but I think there's a significant amount of work that has to be done from a research and a development point of view in order to make it ubiquitous and in order to be able to do that in the CXM. And that seems to be the biggest, to me, that's one of the biggest challenges we have to work with.
I think your question is about dark silicon, right? And people tend to use that as if it's a bad thing. I think dark silicon is a great thing. I wouldn't want my cell phone chip always running, every circuit on it, you would drain the battery. So I think an intelligent application of dark silicon, or turning off blocks that aren't being used so you save power for those blocks that are needed, is a good thing. And it's been one of the important innovators in what we're doing both on our SoC chips, of course, even on our mainstream CPU chips, by doing power throttling of certain blocks when they're not being used.
The thing I want to add is that to the extent it's true, it's always been true. To the extent it's not true, it's not true. But point being that we haven't, there are always usages where you can use all the transistors and there is no such issue where you can't use them, just you have to turn them dark. But at any given point in time, you can always define a power budget, right? You say, look, I want to run this thing at 1 watt. Therefore, I can only use some parts of it, right? But I still need the functionality. So you can create this problem at any point in time. You could have created, right? So it's nothing new.
So can we call
But at least, like I said, we have not run into any, we have not been forced into this at the ends of, at the performance ends that where we need to use our silicons and we have performance benefits from, we are able to use all of them.
So the extent that it's true, it's always been true, and the extent it's not true, it's always been not true.
Yes, it's still not true.
So is that Pradeep's law, or are you quoting somebody else? Okay, Ian, something?
So I'm aware of the paper, and from a point of view, listening to my colleagues, for short term, they seem to have it under control, but from a long term, from the academic point of view, there is talk about addressing the dark silicon if and when it happens, by using very low power switches or transistors. So maybe one of the technologies that we're looking at that will take us to very low voltage will enable us to have very, very low power cores and dark silicon operating. So we're taking advantage of those dark silicons to do real operations at very, very low power. So this is a long, you're getting it? So it's when we add another device to the technology. We're not there yet, but we may do that. And this is what my longer range research is.
You and I need to sit down with Mark sometime and convince him.
Well, let me add that if dark silicon were our only solution for power, we'd be in trouble.
Yeah.
It's a very valuable technique that we do utilize. But in addition to that, we do other power-saving techniques, such as reducing the size of transistors, so it takes less power to switch them on and off, adding low-voltage techniques, such as Tri-Gate. So it's a great idea to include in our suite of power reduction ideas.
Right.
Okay. Great question, by the way. Next question. Hold it. I got to ask. Is it a graphics or a user interface question? And don't play anything.
Oh, it's a user interface anthropological question.
There you go.
Basically straight out pants right.
Well, I'm Paul Mooney from Intune Network. And I'd like to know, is there a society on this planet that actually uses the caps key?
The caps key.
You lock the cap.
You locked it.
Yes. So I should ask that question. So there's a historical precedent for it. It turns out when typos were first invented, they only came in capital letters, so there was no lowercase. So there was in fact an early period where all typewriter utterances came in only one single case, and it was loud, obviously. As we've moved into moments of the caps lock key becoming a facet of, I can't believe you're asking me this question. You actually find there are places where the use of capitalization signals things other than the kind of common notions of etiquette we have, where things in capitals means having a fairly vocal or voluble or angry opinion. In other places, it's used for other things. For emphasis, it's sometimes used to get around the fact that keyboards don't give you full access to the language that you use, and yes, sometimes lock the key that way.
And then there's the E. Cummings, who never used any capitalization or punctuation. He got away with it.
And then there's the wonderful apocryphal tale that says if you have a keyboard in front of you and you look at the top row of letters underneath the number pad, you can actually spell the word typewriter from that single line, which happened because the people who bought the patent for the typewriter, Charles and Lyndon, actually agreed to change 2 letters from the second and first lines of the typewriter in order that you could type the word of the name of the object from its first line, so that when it was taken out to be displayed, you brought a woman and a typewriter and she typed the word typewriter in capital letters, which appeared on a piece of paper and everyone went, ooh! First birthdays.
That was beautiful. Is there anything else you'd like to add?
Fountain of useless information, right here.
Great, thanks, Paul. Next question.
Since Genevieve is on a roll, I have another user experience.
There we go. I don't think I can top the history of boothways, but go for it.
In the keynotes, I'm Scott McInnes from T. In the keynotes, there was a lot of emphasis put on user experience. And my question is that focus new for Intel, and how is it changing the way that you do your business?
You see, I think you shouldn't ask me that question. I think you should ask it to everyone else sitting beside me about how they feel about that question. My answer would be that I really do seriously think there's some other people down there you should ask how they feel about it more than me. I think one of the things that's been remarkable as a social scientist inside Intel for the last 14 years is to watch the way the company has changed when it comes to thinking about, in some ways, what the purpose of the enterprise is. I mean, when Dadi stood up there yesterday and said that, Intel's mission was to touch and enrich the lives of every person on the planet, not only did he mean it, but it sounds very different than things getting smaller and faster and cheaper on a knowable cadence. Those sound like 2 quite different impulses, right? And I think, one of the things that I've certainly seen is that we are having different conversations than we did. But I think it's been a gradual process. I'd say it's been going on for at least 3 to 5 years of thinking about how you start with experiences, about what that would mean for our planning process, what that means for how we think about many of the things we do. But it also means that, although I'm sure you would find it difficult to believe, there are people in my lab who talk to the people at the end of this line here about what the future looks like. And we have conversations about what will people want in 2020 and beyond, and how do we use that to shape the ways we think about architecting our silicon.
Yeah, Ajay, you want to add something?
Yeah, we've actually, borrowed her methodology and implemented that in development of ultrabooks. So we get a lot of user-centric data. So for example, touch on a clamshell. If you listen to a lot of people or the conventional wisdom, they say, well, if you have a clamshell, touch is not very useful. I'm here to tell you that touch is very useful. I'm using a clamshell with touch every day. Sensors and context awareness is another one. Security. Machines get lost because they're mobile and they get small. Identity protection. So the things that you see in standard ultrabooks, or based on some of the studies that we've done. So one of the things that we're doing actually is our market research folks take some of the key Intel, decision makers. For example, Dadi. He was taken to somebody's home in China, and he spent a day with them, observing how they use the technology. I got an invite to go to somebody's home in Brazil. So this is happening, that we have accepted this new approach. And I think it makes a lot of sense, because if you looked at just 10 years ago, or even 7 years ago, every time we came out with a new processor, we talked about the greatest benchmarks. And people didn't perceive it, or they didn't feel it. If you look at all new ultrabooks, just go to the ultrabook zone and start experiencing different things that people are trying. And you'll see direct impact of some of the work that Genevieve and her lab has been doing.
It translates even to fine-tuning. Like, for instance, in the demo showcase, there's a hybrid drive from Seagate that we're sending hints from the Intel driver as to what to cache and not. And rather than use any benchmark, it's all a set of user experiences that we've captured in some cases over the course of 30 days, and we picked the user experiences, and we don't measure benchmark scores, because actually on a cache you can get benchmark scores of exactly the same as an SSD, because almost all benchmarks fit in a reasonably sized cache. But the metric of goodness is how well does it run these user experiences.
Go ahead.
Just to add one more thing, this selfish interest in what Genevieve was talking about. Computing has not hardly done anything for the masses yet. That's my belief, right? So it's barely touched the lives of people. So it's a changing demographics of people. More and more people that we want to make are not yet part of the digital world. Their life does not depend critically on computing. Okay, so one of the big thing that we do in our lab is big data computing. So there's no way I'll ever get the big data that I'm desperately looking for, unless each and every guy was somehow involved in the digital world, not by uploading and downloading photos. No, that's very slow. Where around the clock, without you consciously doing it, data was getting uploaded and downloaded. That's the real big data world that we haven't even seen it. It's never going to happen if there are few geeks sitting in front of a workstation writing SQL queries. That's never going to happen.
Okay, next question. Did anybody who wanted to answer this not get a chance? Oh, here we go.
Working on the graphics and media is actually much more closer to everyday experience when you work with a computer or something. So I think for that sense, all the technology we build actually have direct connection to the world. I think when we built some function like a quick sync video editing hobby, I have personal experience that when I asked my friend to do video editing for me, he said he spent the whole weekend. And asked me again, can you do another one for me? He said no, because it takes too much time to edit video. And that's the user experience. Okay, if I can solve the speed of the problem, so editing HD video, I think I can directly benefit from that technology. I think that really shows that when we introduce new technology, particularly for consumer product, PC or tablet, phone, I think really what people daily life can affect by certain things.
I got pretty excited when the client and it started to look very much like a human. And so all these sensors are getting built in. So is Intel have this coordinated research on all of the sensors? Obviously sight is the biggest one, so graphics, sound, touch, which is a big one. I haven't seen anything on smell. So I would love to hear, and then all of the related sensor research that goes into your system.
All right then. I think this one might be Ajay and I. So between Ajay and I, and I'd say a couple of other places in the company, there's a great deal of research going on what I think inside the company we're calling perceptual computing. So how do you think about engaging with, not just controlling, but engaging with technology using more of your senses than just the keyboard? So how do we think about touch, gesture, voice is clearly in kind of the things that are being done inside the company. There's been a little bit of work done with smell as an interface. Most of it was done in the last 10 years in university research houses. The most sort of successful example I can think of was actually done at the Media Lab about 6 years ago, and it was using smell as a form of ambient display. And so that when you came through the doors of the building, there was a scent cloud that you walked through, and when the stock market was up, the scent cloud smelled of mint. When the stock market was down, the scent cloud smelled of lemon. And people learned as they walked into the building how the market was doing. Now,
you know, in their buildings, there are other kinds of scent clouds. What do you do for those?
I have no comment about those. I think they're not linked to the stock market explicitly.
They could be, who knows?
And yet not so far. So I think the most interesting stuff in the sense space was really about using it as a trigger for activity rather than as an actual interactive space. And well, so I mean, there's plenty of work done on using it in the retail space. I mean, Cinnabon is famous for having actually patented the smell they make in a way of aerosolizing the smell of cinnamon to distribute it in airports. You'll all be familiar when you go into an airport or a mall that has that particular franchise. You can smell it because they've worked out how to fragment the smell and use it as a trigger. There's not a lot for it as an interaction mechanism yet, and I don't even want to go into what taste would look like. I think the notion of us licking our technology is probably quite unfair.
We're capturing the smell and sending it to your friend.
And you are 12 years old, aren't you?
Excuse me?
I said the 12 years.
The whole,
a
few years ago, it was Justin, I think, he talked about this whole area of contextual computing. And we've taken some part of it, and now it is part of Ultrabox. And as we go forward, I believe this whole sensors and context awareness and then fusing hard sensors with soft sensors like traffic, calendar, and all sorts of information that exists in the cloud, and providing assist to a user, when you need it, how you want it is a big and very fertile area. We have a lot of work going on, as Genevieve pointed out, and you'll see this happen in our products.
And so for someone who speaks with their hands, is there any remedy for that?
You should try sitting on your hands, maybe the remedy. I think, all of the challenges we've seen as both in Ajay's lab and mine, and in fact our colleagues Molly Eden's lab, one of the big challenges we see with the next generation of input mechanisms and control mechanisms, particularly in the gesture and touch space, is that you actually have to get consumers comfortable with a particular grammar of those things, a grammar of touch, a grammar of gestures. Fortunately, most of those have been relatively easy to adopt. I think most of us have learned how to use buttons, for instance, and I think, no one walks up to an elevator and doesn't know what to do with the button. The challenge is usually to stop pressing it once the light comes on, which has consequences for how touch gets enabled. We also know that there are interesting issues in the gesture space. Most of us up here weren't raised in the United States, and many of us come from places where a gesture you commonly make is kind of an offensive gesture where we come from. And there are certainly some interesting challenges about how you develop gestures that are effective at a distance from any object. And all of the gesture work at the moment breaks down when you get between the sort of computation on your desk to the computation across the room and you're on a sofa. And I know I've talked about it before, but one of the challenges in that space is really teaching any object that has to recognize gesture how to parse the difference between the gesture of one person and another person. So you may talk with your hands, but if your spouse also talks with their hands, you're now expecting the machine to work out who it should listen to and what it needs to recognize as the input. And I think there's some really interesting computation that has to be done there in order to work out who's in charge of things, so who you should listen to, all of which become challenges as we get into that sort of space.
Okay, Dave.
All right, David Cantor. So this is actually a graphics and server question. And in the context of Haswell, you guys have a long history of excellent encoding and decoding. And I can imagine contexts where that's useful, say YouTube or other places there. Have you looked at taking the video encode and decode blocks and the value that might add in the context of a server architecture?
Yes. We are evaluating that in different ways, based on, again, coming to look at usage, because as people start doing a lot of transcoding and encoding in the cloud, and a lot of those areas, you start looking at trying to evaluate the efficiency of the architectures that we currently have, and with respect to really looking at what should we be doing for the future. So there's a lot of evaluation going on, but no commitment in terms of exactly what directions we'll take.
Ramon, would that significantly change your life in terms of the graphics, architecture, and design if you wanted to slip it into the cloud?
So definitely if you look at the consumer usage from the phone, from the PC, versus the usage in the server space, there are some differences. For example, video format 422. 422 is non-exist in the consumer space. But there are server places people use 422 in the actual delivery of the content. So there are some differences. You cannot cut-paste our solution in one segment and drop it in another one. So you have to look at the market requirement and try to look at if we have a solution for both. And also, there are also technology that people use, like the end delivery of content will be received by the user. For that, is 420. So what you do, either cloud or client or mobile device, the end format has to be the same. So yes, creating the end result, either it's cloud compute or local compute, still requires the same building block, same IP or either hardware or software. I think it's a very interesting topic, particularly when we look at the broader list for mobile device out there. The demand on the cloud to process media content, process graphics will be there, and it's getting bigger and bigger.
I think just to add to that,
Quickly, we need to get to more questions.
Okay. Just the challenge is, how many of those functional units would you put in and what trade-offs do you make with the number of cores that you put in different segments of the market? Those are all the kind of issues that you have to really address to make sure that once it's cast on silicon, you know what the consequences are.
Any thoughts about that transition in the way users access their information in the PC experience?
I actually like to challenge a premise. I don't think it is one device versus other device. The way we live, and there's, by the way, there's a paper that Google just published, and it just came out last week, and I was just looking through this. Actually, what happens is people have multiple smart devices, and they'll have more and more smart devices. So it's all about getting access to information. It is less about computing, but getting access wherever I am, whether I'm on the car, on a train, or wherever I am. I want to get to my information. And when it comes to information, there are two models that they talked about. There are models in which there is a sequential model. You start in one place and continue in another place. Or there is a simultaneous model where I'm watching TV and I also have a laptop with me or a tablet with me or a phone with me. So that's where I think that's how things will evolve. I don't think it is one or the other, but it is just portability, and then you'll have adequate experience, or just the right experience for the device that you're using.
Yeah, I think the data currently, and my sense of where it is going, is that we're going to have, at an individual and a household level, multiple devices. I think it's fairly clear from all the work we've done recently that people have a kind of an ensemble of digital devices that move with them and that they visit at different points of the day, right? There are phones that are in everyone's hands and under their pillows when they sleep. There are computational objects that go to the office, that go to school. There are computational objects, whether they're smart televisions and desktops and even laptops that you go visit. And our sense from spending time with people is that people are actually, as Ajay says, they're in fact doing multiple different things across those devices across any given day. And there are devices that people like better for certain kinds of activities. There are devices that people have different kinds of, in some ways, emotional relationships with and different feelings about. But when we've asked people, what can we take away from you? When you say to this group, right, we're taking you down to one object, what's it going to be? You'd be amazed, it's mostly not the telephone. If you suggest to people you're going to take away their television, that actually generates a level of anxiety far beyond the level I would have expected given, the number of other devices that are available to people, right? So we see a whole range of them. And frankly, I actually thought Ajay was going to push you in a different place, which is, I think, if I listen to Pradeep's and, Faye, who hasn't said anything about it, reasonable injunctions here that there are places in the world where connectivity is not yet so pervasive that you could have everything in the cloud, and where the device ownership pattern looks completely different to the one that it looks like in this room. And oh, by the way, those are going to be the markets that matter 10 years from now. And they may not have solved notions of constant connectivity by then, or the kind of bandwidth we've seen in places like this over the last 5 years. I think we're going to actually see the emergence of some very different models of computation, whether it is more data on the device, asynchronous connectivity, where you're only connecting to clouds of information on a semi-regular basis, more notions of local storage, whether that storage is house-based or community-based. It's certainly the case in most parts of Africa and indeed many parts of India that where consumers do have smart digital devices, they own some but they're accessing others that are in communal locations, all of which has completely different implications for how you architect the cloud, how you think about security, how you think about forms of connectivity, about how data gets moved, about what data moves and under what circumstances. And I actually think when we look 5 to 10 years out and we think about where the major technology markets are going to be, China, 1.3 billion people, 800 million mobile phones, 500 million online payment structures. India, 1.3 billion people now, 850 million mobile phones. 1 billion people in Africa, only 100 million mobile phones, but a fairly big growth ramp there. Those are going to be places where my suspicion is what it means to talk about technology and a digital life is going to unfold in radically different ways, with really interesting implications for stuff we all care about.
This is not a third or fourth generation of processors, which are quad-core and no more. It's nice to see the sort of bigger AVX processor, but do you feel that desktops will never go beyond 4 cores, or what's happening? The trend seems to have come to a grinding halt.
So I think if you look at what goes into high-end desktops and workstations, what we do is we let the client line and the server line overlap slightly. So there is actually a lot of high-end desktops that use the server silicon, and they, through that, get a higher core count. So what we've done is just sort of try to pick the right spot to have the overlap by a smart amount, and by doing that has allowed us to stay at 4 cores for a fairly long time. Does that make sense? So it's more of a making use of the 2 product lines we have.
First of all, I'd like to give it up for the people on stage. I think they did a pretty good job. And I'm going to leave you with one thought. If it's right, it was always right. And if it's wrong, it was always wrong. 2012.